In this video, we will look at process capability measurement. And this is the ability of a process to produce output that conforms to the specification of the customer. We will look at the similar histogram like we looked earlier and look at the voice of the process, what the process is actually capable of doing. The histogram shows us the collection of the sample of the measurements of the particular characteristics that we were looking at. Let's assume that the customer really wants to have, let's say it's a diameter of a particular product or a length of something. And let's say that they would like it to be 6, the value of 6, whether it's centimeters or millimeters or whatever it is. And they have a tolerance. They are willing to accept anything that is going up to 10 or the lowest at 2. So that will be considered as the voice of the customer. These are the requirements of the process, that the lower specification limit will be 2. So we want everything to be above 2. And the upper specification limit is going to be 10. So the specification limit are the voice of the customer, and the histogram, the sample, what we actually see and observe, that's the voice of the process of actually what it is actually doing. So let's look at the voice of the customer and see if we can provide a measure that is looking at whether we are satisfying the customer requirements or not. So anything that goes above the upper specification limit will be considered a defect. So anything that goes under the lower specification limit will also be a defect. Obviously what we want is to lower the amount of defects that we have. So we're going to look at a measurement of the capability, and we're looking what's the ability of the process to meet specification. And we're looking at an index that is basically the ratio of the specification range and the process spread, which determines the standard determined by the standard deviation. So we're going to call it a capability ratio or capability index that is looking at the range of the specification from the customer divided by the spread, which is 6 times the standard deviation. So again, in this example, the lower specification was 2, the upper specification was 10. So the spread of the range of the specification from the customer is 8. And then we will look at an example that the standard deviation is 2. So let's assume that we have a standard deviation of 2. So this is what our process is doing. That's the blue line. And we're looking at the capability index. So we're going to look at the spread of the requirements from the customer, which is 8, and divided by 6 times the standard deviation. So we have a range of specification, which is 8, divided by 6 times 2, and we get a value of about 2/3. That's going to be the index. If we're looking at the probability that will be out of specification, that will have defects, that's the area that is above the upper specification limit and under the lower specification limit. We can use some statistics. All of this is coming also with software, which will have this information, but just so we'll know where it's coming from. The probability is the area under the curve. So in this case, the probability of being under the curve above the 10 is the 2%, 0.275. Similar, because of the symmetry, we have the same under 2. So the probability that we will not meet specification is the sum of these two values, which is about 4.55%. So if we look at the measure we did in Module 1, which is the defects per million opportunities, if we're producing 1 million parts and we know we have about a 4.55% that we will have defects, that means that we'll have 45,500 defects out of the million. Let's look what happens if our standard deviation instead of 2 is going to be a 1. In this case, the index is going to be 8, which is the range of the specification, divided by 6 times 1, which gives us 1.333, which is 4/3. And in the probability of being out of specification, you see that the area under the curve that is above the 10 or under the 2 is much smaller. In this case, the probability, I don't want to say all the zeros because I'm probably going to miss a 0, but you see that the probability is very small to be above the 10 or under the 2. So the probability to be out of specification is the sum of these two, which is this value. And if we look at how many defects, if we're producing 1 million, what are the defects per 1 million? Take this probability times 1 million, we get that out of 1 million, we will have 64 defects. So if we're looking at the two examples together, we see that we have, this is when the standard deviation was 1, and this is when the standard deviation was 2, with everything exactly the same range for specification. So the convention that we have is that if the capability index is less than 1, then the process is considered incapable of meeting the specification requirements of the customer. On the other hand, if the index is greater than 1, it's considered capable. That being said, if the index is exactly 1, it means that there's no room for more variation. Therefore, in practice, practitioner considers 1.33 to be the minimum acceptable value for capability index to determine if the process is capable. Anywhere between 1 and 1.33 means that the process is currently okay, but it has a chance of being incapable if any variation gets involved in the process. Think about a similar kind of gray area if, let's say, somebody has a temperature that is 99.9 degrees, then you know that this person is not, you don't say immediately they're sick, you can even probably send your kid to school if it's under 100, but it's an indication that maybe something is wrong with the person. So this is this gray area that that it's kind of okay right now, but something might happen. So similarly, if you have, let's say, an index of 1.1, theoretically it's above 1, you'll say it's capable, but that it's really, probably not going to be capable if there's any more variation introduced into the process. So therefore, this, that's why practitioners are using the 1.33 as the point where we say that's when the process is capable or not. If the process capability is 2 and above, that's when we were going to say that the process is Six Sigma compliant. So let's look at one more concept, and we will look at an example where we're going to look where we still have the specification limit of 2 and 10, but the mean of the process, we have 112 samples, the mean of the process is 6.024, and let's assume the standard deviation is 1.724. So this is just an example of a process. And if we're going to do the process capability index, the spread is still 8, 6 divided by 6 times the standard deviation, we get an index of 0.773. We can calculate the probability of being out of specs, and we see that the defects per 1 million is the DPMO is 20,343. What will happen though if we take similar requirements and a process with a similar standard deviation, but the mean of the process now is at 7.524 instead of the 6 that we had before. So now we have, again, 8 divided by 6 times 1.724, we get the process capability of 0.773. So it looks the same like we had earlier. However, when we are looking at the number of defects using the probability, we see that the DPMO number of defects per million is 76,150. So if I summarize the table, and we're looking now at the last 2 examples, we have a mean that it shifted by 1.5 standard deviation. So the standard deviation is the same. In this case, the capability index is the same, but we see that the number of defects is much higher when the mean shifted. In other words, what we see here is that the capability index, as we calculated it, doesn't take into effect that we have a different mean. So it's not, if you remember the formula, there is no place where the mean comes into place. We're taking the spread of the requirements from the customer divided by 6 times the standard deviation. So if the standard deviation is the same, we will get the same index. So we would like to somehow have a, kind of like this benchmark, something that is telling us, the center has shifted. And therefore, we're going to use what's called one-sided indexes to look at how the process is in relation to the center. Are we spread, around the center and with nice symmetry, or we shifted to one side or another? Okay, so in this case, we have the one-sided index. We have an index for the lower side and an index for the upper side. The lower side is looking at the mean minus the lower specification, and this time divided by 3 times the standard deviation. And similarly, the upper side index, CPU, stands for the upper, is the upper specification limit minus the mean divided by 3 times the standard deviation. The worst case scenario is the worst of these two values, so we take the minimum between these two values. Let's look at an example. Go back to the example where the mean was 6.024. So the CP we know was 0.773. Now let's do the one-sided index. So the lower index is the lower, the mean that we have minus the lower specification limit, and we divide that by 3 times the standard deviation. And in order to find the CPU, the upper side index, we take the upper specification limit of 10 minus the mean divided by 3 times the standard deviation, and we get this index. The worst case in this case is 0.768. In both cases, they're very close to each other. Okay, they're also not very far from the index that is not one-sided, the one that doesn't take into account the mean. And in this case, we already know that the DPMO is about 20,000. Let's look, however, at the next example where the mean has shifted to the 1.5 standard deviation. So the mean now is 7.524. The lower specification, the lower index is going to be the mean minus the 2, and we get an index of 1.068. And we're looking at the upper index. It's 10, which is the upper specification limit, minus the mean, 7.524, divided by 3 times the standard deviation. We get a value of 0.78478. And the worst case in this case is the 0.7478. Visually, you see that the problem, you have more defects on the upper side because the process shifted, the mean shifted to the right. We have more probability of having defects because we don't satisfy the requirement of being above not to be above the upper specification limit. And in this case, we see that when we're looking at the number, the DPMO, we have 76,000 defects per 1 million. So in this case, we see that the process is more likely not to satisfy the upper specification limit, and the one-sided indices and the CPK, which is the worst case scenario, provides us with this information. Let's look at another example. Suppose that we're looking at the wait time in a cash register of a major supermarket. And let's assume that it's the wait time is normally distributed with a mean of 4 minutes and a standard deviation of 0.75. And let's assume that the specification for the customer, for whatever reason, they have a specification of 4 plus or minus 2.7. In other words, no more than 6.7 minutes, and for some reason, they don't want to be less than 1.3. Maybe they think they don't get enough attention. So we are looking at the index, the capability index at 6.7 minus 1.3. That's the spread. Divided by 6 times the standard deviation, we get a 1.2. If we do the one-sided indices, we know that the mean was 4, so we can calculate them. And again, we're getting a 1.2. The minimum case scenario is 1.2. And in this case, we have that the one-sided index equals to the capability index, which is 1.2, and we see visually that it's all symmetrical. It kind of like goes with this kind of scenario. So we will say that in this case, the process is centered and capable. Although in practice, we want it to be above the 1.3, but theoretically, let's just assume that the 1 right now is what's telling us that it's capable. Okay, now let's see that the mean shifted from 4 to 4.7. Again, we're going to do the calculations. The capability index is still 1.2 because the spread between the specification limit didn't change, and that this capability index does not take into account the mean. And when we do the one-sided indices, now the mean comes into account. And when we calculate them, we get a 1.5 and a 0.88. The worst case scenario is 0.88. Therefore, the capability index, that's when, if it's not equal to the capability index that is not the one-sided, we will use the CPK is to determine whether it's capable or not, because this does not give us the indication of where the center is located. So we use the CPK. We know that it's not centered. We can see that visually. It's also because if the CP and the CPK are not equal, that tells us that they're not centered. And we see visually that it shifted. So in this case, the CPK is what tells us whether the capability of the process, and it's under the 1, so we know that it's not capable. We see that we have more defects on the right side also. And we know that the process is not centered and is not capable in this case. Let's look at one more example. What would happen if the standard deviation, instead of being 0.75, was 0.3? Visually, you will see that the spread of the process, if we're looking, it's much more, it's closer to each other because the standard deviation is smaller. Again, we will calculate the indices. In this case, the capability index is 3. Looking at the one side, because we do see visually that there was a shift, we get, we're taking into account the different standard deviation. We're taking into account the mean of the process, which was 4.7. And in this case, the CPK is the worst case scenario, which is the 2.2. It is greater than 1, so we know that the process is capable. However, we see that it's not centered because the capability index without the mean, CP, is 3, and that is not equal to the 2.2, which is the one-side index. So in this case, the 2.2 is what's determining the capability, and we will say that the process is not centered, but it is capable. So when we're looking at a capability index study, we were going to look at the variability in the process. We will look whether the process is centered and what is the performance relative to the specification of the customer, whether it's acceptable or not, what proportion of the output is expected to meet specification versus those that don't, which will help us determine the defects per million, and then understand, the next step will be to understand the factors that contribute to the variability. When we're looking in general, we see there's industry determine what is a sigma level. We want to be at a 6 sigma level, which means the process, the CP should be a 2. If we're looking at the CPK, it should be 1.5. It can be proven statistically, although it's beyond the scope of this class, that would, when we have a CPK of 1.5, the number of defects per million will be 3.4, and you will work a little bit on this in another tutorial. So in order to be 6 sigma compliant, the process, the CPK, even when it shifts 1.5 standard deviation, the defect per million will be less than 3.4, which will determine that it's 6 sigma compliant. So just to recap what we did in this module, we were looking at control limits that are calculated based on the data from the process. That's kind of like the voice of the process. And the specification limits is what the customer wants, taking into account the tolerance that is acceptable. And this is what's called the voice of the customer. We were trying to reduce variation so that we will have a stable process and the customer will know the expectation exactly what they're getting and that it will be meeting what they want. So we use control charts to get any signal about special cause of variation. We take action at the operation level to make sure that we have a stable process. If the process is in control, we know we have no special cause of variation, and any variation is due to common variation inherent in the process. In this case, we'll do a capability analysis to determine, to capture the voice of the customer, understand whether we meet the requirements of the customer or not, and if our capability analysis shows us that we don't, we need to address the common cause of variation. Thank you.